This is a very good topic for you to be reviewing for your exams because it appears almost every single time. It is very common to have questions about this. And while it is a relatively straightforward topic, it does have a ton of little tiny details of things that they want you to know specifically and do things in a specific way. And if you don't remember all of those details, you will fall for the trick questions, and we don't want that. So today I'm going to start by quickly covering the basics of what this is all about, and then I'm going to go on to focus on all of those tiny little details. So first of all, imagine that you have a data set about something that interests you. In my case, I really like data sets of students' grades. I like looking at how my students are doing at tests. So if I have a big list of my students and all of their grades, there's a bunch of things that you already know how to do with them. You can make a histogram of the grades, for example. I could look at a box and whiskers graphs of those grades, or I could put them in a cumulative frequency graph. And those are all very good ways of visualizing data. But now say that I am not only interested in my students' grades, but I also want to know, say, how tall they are. So I could ask all my students, I could put that information in my spreadsheet, and I could do all the same things again. I could make a histogram and a box and whiskers and a cumulative frequency graph. So now I have two variables about my students. I have their grades and their heights, but I don't know anything about whether these two things relate to each other at all. Are the taller students the ones who are getting the better grades, or is it the shorter students, or does it matter at all? And I probably have a little bit of all of those things in my class, right? I have some tall students who are getting good grades. I have short students who are also getting good grades. And I have some short students not doing so well, but also some tall students not doing so well. Of course, you wouldn't expect how tall a person is to influence their math grades, but the important thing here is to understand what we are looking at. This type of graph is called a scatterplot, and it is the way to visualize two pieces of information about people, in this case, at the same time. So each one of these blue dots represents one of my students, and as points in the coordinate plane, they have two coordinates. Their horizontal coordinate is representing the grade that they got on the test, while at the same time, the vertical coordinate of the same point is representing how tall this person is. It looks like the points are all over the place because they are. There is no connection between people's height and their grades, but other times you are asking more interesting questions, such as a scatterplot between how much time people studied for the test and the grades that they got on the test. Now that is something that sounds like it would be more related than height, which is why I'm showing you a scatterplot in which this does look like it's going on. Like the people who studied the most or points more to the right on the graph, they are also higher on the graph because they got better grades. Of course, it is not perfect. There are exceptions. There are these two people here who studied almost nothing but went well anyway. This person was probably disappointed by their grade given how much they studied for it because he got a smaller grade than other people who studied about the same as he did. But these things happen, right? These correlations are never perfect. You do see a general trend of something going up like an increasing function, but it's not perfect because it is data collected from the real world. Now, the reason why you would do something like this, why you would collect this information and plot this graph, what are you trying to learn by looking at the correlation between study time and grades, is because you want to be able to predict how one thing influences the other. You know that this is more or less what happened the last time, and you also know how many hours you studied for the next test. So you kind of want to have an idea of what kind of grade you're going to get. But how are these points going to help you to make such a prediction? Because they are not perfect. They are not on a line. So what you want to do is to put a line through them, but you want to do it in the best way possible, the way in which the line mostly resembles the point that you're seeing. So for this graph, something like this maybe. I'm just doing this by looking at the points right now, okay? This is incredibly imprecise. In a moment, I will show you how to use technology to get the actual line that goes best through the points, which is going to be called the line of best fit. And it is this line that you would use to predict your grade if you know how many hours you studied. You would take that value of x and then look for the y value of the line, not of any individual points, because the points have differences between them. You want to predict based on the general trend created by the points. And speaking of x and y, did you notice how here I put study time on x and grades on y, but in the previous graph, the grades were on x and the height was on y. So how do I choose where to put each one of my two variables? Well, it's about the predictions that you're trying to make. In the case of grades and height, I wasn't really trying to make any prediction because I know that these things are unrelated. So I am not going to just look at a grade a student got and be able to imagine how tall he is. But I am also not going to be able to look at a person, see how tall they are, and based on that, make a prediction of what grade they're going to get. So this doesn't work either way for prediction. So in this case, I just chose randomly. I put one of them here and the other one there. But for this one, I had a very specific purpose in mind. I wanted to be able to ask myself, how much did I study? So based on that, what grade do I think I'm going to get? That was my intention with this graph. So that is why I put the study time on the independent variable and grades on the dependent variable. Because this is how these things work with functions and graphs and stuff. You don't even have to be talking about scatter plots and data, but any function that you have, and in this case, the function that I'm talking about is my line of best fit. This is how these things are supposed to be used. You have f of x, right? So f of x is f of a value of the independent variable, and that gives you f of x is a value of y, which is then like an answer. So you predict this value based on that value. Of course, with functions, you can also ask the opposite question, like if somebody got this grade, how much do you think that they studied? Like this from a teacher point of view is also an interesting question, so I could have done it the other way around. But it's just one of those things to keep in mind. I'm going to come back to this topic later about who is independent and who is dependent. And also if you're using this for your IA, which is really, really common to use some type of correlation in IAs, make sure that you make the correct choice. Like out of your two variables, which one are you thinking is having a cause and the other one is being a consequence of the other? Because you had better put the cause horizontally and the consequence vertically. Not only put them in the correct places, but also in your IA, write out a sentence about this choice. Make sure that it wasn't just luck that they fell into the right place, but that you show the reader of your IA that you know what you're doing, that you have to make this choice. But anyway, I don't want to talk about IAs today. I want to talk about exam questions. And there are many types of questions that they ask you about this. And I'm going to begin by talking about when they ask you to describe one of these things. Describe the correlation between study time and grades. Now, when they use the word describe, it is never a thing of putting it in your own words and saying whatever you want. That's not it. They say describe, it sounds vague, but you're supposed to know, because you studied for this test, what they want to see as an answer. And in the case of describing a correlation, there are 4 things that they want you to talk about. The first one is that they want you to say if the scatter plot looks linear or not. Does it look like it could fit a line through it? So I have 2 examples here, and I think the first one is pretty clear that we can see that a line would go through that, like this. See, it's a very good line. But the other scatter plot on this page doesn't look like a line. It looks like it is accelerating. It starts going up slowly and then it's going up faster. I can try to put a line through it, but it's not going to look very good. The natural thing that you imagine going through these points is something a lot more like this, right? So it's non-linear. And that is the first thing that you have to mention when they ask you to describe. You say it's linear or it is non-linear. I said that it's the first, but it doesn't really matter in what order you say the things, okay? Just as long as you know that there's 4 things to be said, and this is one of them. Linear, non-linear. The next thing that you want to mention is direction, because these are functions that are going up and these are functions that are going down. So increasing and decreasing, because correlations can go either way, right? When something increases, it can cause something else to go up, but it can also cause it to go down depending on what the things are. For example, if you study for more time, you expect your grades to go up. However, if instead of study time here, this was how much time you spend on your phone each day, like you're not doing anything else because you're just constantly scrolling, so the more you do that, you expect to get lower grades on exams. So this graph would be going the other way. And this is the second thing that they want you to mention when they say describe. It's direction. This is increasing, this is decreasing, and the word that you're supposed to use is that these are positive correlations and these are negative correlations. The third thing is going to be strength. And what does strength mean? You see this one, how good the line of best fit is? All the points are really close to the line. This is a strong correlation. These don't look as strong as that. The points are more spread out. So you see, we start to get a few points that are far away from the line. And on this one, you get points that are even farther from the line of best fit than in the previous example. So this is what it's meant by the strength of a correlation. It's how far or how close the points are to the line of best fit. And then you can use words like strong, weak, moderate, very strong, or moderately weak, or something like that. And just be careful with a common mistake here. I hear a lot of students describing strong correlation as a lot of the points are on the line, and that is not what the definition of strength is, okay? So even in the weaker one here, I do have some points that are very close to the line, but it's not about how many points are close to the line. It's about the general trend of where all of the points are. And this one has many points that are far from the line. There's always going to be some points close to the line because the line is intentionally going through the middle. So of course there are some points in the middle. And the fourth and final thing that you want to include in a description is the presence or absence of outliers. Of course, you've heard this word outlier before in a different context. When we were talking about box and whiskers graphs, there was something very precise to be done when asked about outliers. A whole thing about taking the IQR, multiplied by 1.5, and then, a very precise calculation. But here in Scatterplots, it's not going to be the same thing. It's not going to be a precise calculation to be done in order to say if your scatter plot has outliers or not, but it's still the same idea of a point that is very different from the trend, something that is very far away from where most of the data points are. So for example, here I have a linear strong positive correlation, and I am going to include two more points here for us to talk about outliers. Here are two new points that are far away from the other points. And here is one of the details that you have to be careful about, because one of these purple points is an outlier and the other one is not. Even though both of them are far away from the blue points, which are most of the points, one of them is an outlier and the other one is not, because it is not about being far away from the points. An outlier here is going to be about being far away from the line. We can't see the line right now because it's not here. But when I include the line of best fit in the picture, you see that the purple point on the top is actually very close to the line. He is not an outlier. However, this point here is very far away from the line. So that is what's considered an outlier in a scatter plot. And there is no calculation, okay? People get nervous at this point, but how far away is too far away? And you're going to have to just guess and visualize. This one is clearly far away. This one is a lot more ambiguous. I could say that these two are outliers, but I'm not quite sure about this one. He looks a little bit different from the other points, but is he different enough that I would call him an outlier? Let me know what you think about this example, but you don't have to worry too much about this because the IB questions tend not to ask you about ambiguous situations. The ambiguous situations could still happen in your IA, of course, because real data sets will have these strange things. But the next thing I want to do in the video right now is go to the calculator and show you specifically the instructions for how to get the equation of a line of best fit, and at the same time, how to get a measure of strength. Because we've been talking about strength here in a qualitative way. Is it weak? Is it strong? And we also want to turn that into a quantitative thing. We want to put a number to measure the strength of the correlation. So this thing about a qualitative versus a quantitative statement has a lot of parallels in other things. For example, you can say that one thing is far away from another thing, or that it is close to another thing. So far away and close are measures of distance in a way, but they are qualitative. They don't say exactly how far. They just say close, far, more or less far. But when you want to put a number to that, you want to make it a quantitative statement about distance, then you say it's 3 kilometers or something like that. It becomes a quantitative measure. That's exactly what we don't have yet for these things, for the strength of the correlation, like we did for distance in the example. But we are going to get that. The calculator is going to give us a quantitative measure of the strength of the correlation. Right, so the first thing that you need to do is to give the calculator the points for your scatter plot. So you're going to go here, stat, edit, and you're going to put your numbers there. I've already done that. So remember, this is a bivariate data set. You're going to be comparing two things like study time and grades. So you have two columns. You're going to put the numbers for one of the variables in L1 and the data for the other variable in L2. Now, the next place that you want to go to calculate your line of best fit is here, stat, calc, and then linreg. Linreg is linear regression. So linear because we're going to put a line and not another type of curve. And regression is the name of the process by which we find such a best line to put through the points. Now, I recently posted another video where I had some reason to show you how to calculate a line of best fit by hand. So there's a link to that in the description, but that is completely out of curiosity, okay? You are never, ever, ever going to be asked to do anything like that in an IB exam. What you're going to do is this. You come into the calculator and choose linreg. Now notice that there are actually two linregs. There's ax plus b and a plus bx. I will ask you to please always use the same one. So just because you're going to confuse yourself if you use sometimes one and sometimes the other, the literal only difference is the name of the variable for the slope and the name of the variable for the y-intercept. In the other one, they get switched around. I do not know why this calculator has that, but anyway, I'm going to use this one. So here's where you tell him who is the independent variable and who is the dependent variable. This is going to come up in a lot of the questions. The way that they phrase the question is always going to have a context, like how many ice creams I'm going to sell versus how hot the day is, or something like that. And in this particular example that I just remembered, it is very clear who is the independent variable and who is the dependent variable, right? It is the temperature that influences how many ice creams get sold. Selling more ice cream doesn't make the day get hotter. It is the other way around. So in this example, there is a very clear distinction between who is independent and who is dependent. My example is just numbers, so I'm just going to put L1 and L2 randomly. But other times in questions, he specifically tells you which one he wants. So he says x as a function of y, or y as a function of x, if x and y are the names that he gave to the lists of points in the question, which it's not always the case. Sometimes it's p and t or a and b. He can choose different letters. But if he tells you that he wants p as a function of t, then in that case, p is the dependent variable, and you should put it in the y list to be vertical. And if you don't know how to change that, here is where the things are. The lists are above the numbers, okay? So above the button for the number 1, you have L1 in blue. Above the button for the number 2, you have L2, and so on. So if you wanted to put L2 here, you can just do second and L2, and then go to the other one and put second L1. I don't really want to do this for this example though, so I've just switched them back to L1 and L2. And the next line is also very important. It is asking for a frequency list, which in this type of problems, we are almost never going to be using a frequency list because each point is its own point. It's never going to be like he gives us one point with two coordinates and then, oh, but there's three of this same point. This doesn't really happen. But as for the calculator, sometimes what can happen, and this is weird, but it is just what happens in the calculator, is that if you were previously doing something else in another calculator screen, like if you were, for example, in the one var stats screen and you were using a frequency list for that, for calculating the standard deviation of something from a frequency table, also something that's very common. Then sometimes if you've just been doing that, when you get to this screen, there will be a frequency list here. And you have to just pay attention to that and make sure you remove it, okay? The button for removing it is this one, the clear button. And then you take it away. Okay, so technically we're ready to come down here and click enter, ask him to calculate the line of best fit. But there is something else that I'm going to want to do first, because the next screen after I click calculate is going to tell me the answer. It's going to tell me y equals ax plus b, where a is this number and b is that number. I can write that down on paper and give it as my answer. But very frequently, the next item in the question, like a part B or a part C, is going to ask me to make a prediction using that line. Like we were talking about before, oh, if I study this many hours, then what do I expect my grade to be in the exam by using the line of best fit? So that is a very common question. And because of rounding and approximation errors, I don't really like using the numbers for A and B that I wrote on paper with three significant figures. I may be overthinking this, but I feel like I am losing precision and I don't want to do it this way. So let me show you a very interesting thing that the calculator can do. This line here, store regression equation, okay? You can tell her to not only show you the A and B on the screen, but to actually store the equation of the line of best fit into one of those y equals functions that you graph. So the way to tell her to do that is to go into alpha F4 here and then choose whichever one you want. As for the calculations, there is no difference. If you choose one or the other, you know the y equals button is just a list of functions and all of them are going to get graphed anyway, so it doesn't really matter. But I have a tendency to put y2 because I know that when I graph y2, it's red, so I think it's pretty, and that is literally the only reason why I'm doing this. So calculate, and here is the line of best fit. It is as simple as that. But I told you that we also want a quantitative measure of how strong the correlation is. And the thing is that this screen is supposed to show us that as well. But right now it is not showing us because I want to show you that there is something to configure in the calculator so that it does what it's supposed to do, okay? So that you need, if your calculator is not showing you the strength of the correlation here, if it's just showing you the line of best fit, so you want to go into the mode button where you can configure a whole lot of things, but the one that we want to do right now is this one, stats diagnostics. We want this thing to be on. And now I'm going to try the linear regression again. Stat, calc, linreg. I'm not going to change anything here because I've already stored the equation, so I don't have to redo it. And now here it is. The line of best fit is still here, but now I also have this value of R. R is what they call the Pearson's product moment correlation coefficient. It is a ridiculously long name, but we don't need to use all of these words every time we talk about them. We can just say Pearson coefficient. And in my case, I'm getting 0.835, which is a kind of a large number if you consider that the highest that the Pearson coefficient can ever be is 1. This is a number that always goes from -1 to 1. When it's 0, it means that the scatter plot has the points all over the place and you can't see any clear correlation at all. If it's more towards the extremes, like -1 or 1, it will mean the opposite of that, that the points are perfectly aligned on a line. The positive one will be an increasing line and the negative one will be a decreasing line. And anything in between that is just in between. So I have kind of a 0.8. It is a positive linear correlation, which is strong or moderately strong, if you want. See what I'm doing? I'm describing with the words that I mentioned before. And I don't know if there are any outliers unless I look at the scatter plot, but I've said all the other three things that I'm supposed to say. Now, there are some websites out there that tell you to memorize like strong correlation is above 0 point whatever. I don't agree with that because these things are not clear-cut lines. And again, the IB questions don't tend to ask you about ambiguous situations. So whatever he's asking you about is either going to be strong or weak, or sometimes it will be very strong. But it's not ever going to be something where you are in doubt, like, oh, 0.83 versus 0.84. It's never as ambiguous as that. You start to get a sense of what these numbers mean for strength as you look at more and more examples. So I happen to know that 0.835 is kind of strong. And if you're not sure, you can always look at the picture. I'm going to show you how to get a picture out of this. But first, let me mention that the thing that we just did with going to the mode and turning on the stat diagnostic, now that you've done that in your calculator, it's just going to stay on. You're not going to have to turn it back on every single time you do a regression. But it is still very important that you know how to do that and that you know that that needs to be done. Because at the time of your exam, when it actually matters, when your calculators get reset for the exam, this might turn back off on its own at that moment, so you need to be able to turn it back on at the exam. That is a very important thing for you to know how to do. But the next thing that I'm going to show you how to do, which is how to actually get the calculator to graph the scatter plot, that is not as important because I can't remember having seen a question that requires you to do that. Most of the times, the questions can get answered just by looking at numbers. And when he wants you to do something visual with the scatter plot, then the scatter plot will come printed on the exam in the question. So I haven't seen a question that requires you to plot a scatter plot in the calculator, but personally, I like that I'm able to do that because I'm very visual about math. I like to be looking at things a lot. So I'm going to show you how to do that. It's not surprising that the graph is going to come from the graph button, but this is just the line of best fit because when we said store the regression equation into y2, that's exactly what he did. So here is the regression equation. He's even put more significant figures here than he had on the screen when he was showing me. So that's why I like to do it this way. It's a lot of precision for predicting values. So of course, he has stored it here in y2. So of course, when I click graph, the line of best fit is here. But the points are not, because I need to tell the calculator that I also want her to put points. And that I'm going to do here in second stat plot. There are 3 different statistical plots that you can use. Why 3? Well, just because sometimes maybe you want to configure one in one way and the other in a different way. I'm just going to use one of them. You see how they are all off right now? I'm going to go in and turn on this plot one. And there are a bunch of options that you can use here. As for the type of graph, it is Scatterplot is selected. So that's exactly what I want. So I'm not going to change it. But you can see that he knows how to do other things too. Okay, so this might be useful if you want to explore it. Just like in the linreg screen, you have to tell him L1 is the X list, L2 is the Y list. You get to choose what kind of symbol you want him to put on the screen and also what color. Blue is fine. So now that I've done that, I should expect to see the scatter plot and the graph with the line of best fit going through it. Everything is very pretty. A very common problem that I see people having here is that they say, well, my scatter plot is not showing, but it's a very simple solution because they just forgot to look at the size of the numbers. And in my case, all numbers are in the 200s. Well, no, there is one that is 188. So it's the same thing as in functions, you guys. You have to come into the window and pick a window that includes the points that you want to see. That's often the case when you're not seeing your scatter plot. So remember when I said that 0.835 was kind of strong? Now we're looking at it and we can confirm, yeah, this is kind of strong. it is not very strong. The points are clearly on the line, but there is some distance between some of the points on the line. Okay, now that we've done all that, we can already answer what are probably the first couple of items in a question about this topic, which are going to be find the equation of the line of best fit, find the value of Pearson's correlation coefficient, and then very often there is a next item that says, now use this line of best fit to predict the value of the dependent variable when the independent variable is equal to some value that they give you. And I already mentioned that I don't really like just using the numbers that I wrote down on paper in order to do that, because I feel a little bit weird about approximation. So instead, what I'm going to do is to use this line that the linreg stored in the y equals for me, and I'm going to use that to calculate the value. So in this example, pretend that he's asking me for the value of y when x is equal to 230, okay? So what I'm going to do is get in this menu, second calc, I'm going to ask for the value when the x is 230, and there's the answer, 235. So I prefer doing that because, as you can see in the top of the screen here, the calculator is using a whole lot of significant figures, so I feel more comfortable. Here comes another one of the tiny details that they are always going to ask you about just to see if you know about it, okay? So pretend that instead of 230, he had asked me for 260. It sounds like it's going to be exactly the same thing with a different number. So I go in here, I put the 260, and I get 257 as an answer, okay? Exactly the same process. However, what you can see in this picture is that this time the number that I am predicting is outside of the scatter plot. Like all of the points are here and my new point is over here. In the previous example, when it was 230, the points were here and 230 was somewhere in the middle, okay? So that is a very important distinction that they want you to make when you're using the regression line to predict a value that is within the range of the data points versus a value that is outside the range of the data points. Of course, here I can see it very clearly because I went to the trouble of plotting the scatter plot, but you don't have to do that. It's completely possible to figure out whether a point is inside or outside by just looking at the numbers that the question gave you. Make sure you're looking at the correct list because both of them are not going to have the same numbers. The words that they want you to use for that are interpolation and extrapolation. Okay, so when the value is inside of the range, which was my 230 example, that is called interpolation. When you use the regression line to predict the value for a number that is within the range of the data set. Now, when you want to use the line to predict a value outside of this range, the name for that is extrapolation. And the exam question is often going to give you a value such as 260 and ask you, can you do this? Can you use the regression line? Why not? And you're supposed to say, you can't do it because extrapolation is not reliable. That is a predetermined answer to a question, okay? Don't invent another answer. Whenever they give you a value outside and ask you if you can do it, the answer is no. The justification for the no is because it is extrapolation. Now, I want to say something else. This is very clear cut in exam questions. They will never want you to do an extrapolation. Instead, they want you to say that you can't do extrapolation. But in real life and possibly in your IAs, that is not quite the case. Saying that you can't ever do extrapolation because it's wrong in all circumstances is way too much of an exaggeration. In fact, most times that we are doing regression, we want to do that in order to predict the future. Our independent variable is often time, and the other one is something that we are studying that changes with time. So like we have the data points that we have the trend of how these things are growing, and we want to predict the future. This is very useful. Of course, when we do that, we have to be aware that we are doing an extrapolation and that this can be kind of dangerous because trends that we see around a certain period of time may or may not continue in the exact same way forever. So the farther you get into the future, the less reliable your predictions are going to be. But that's not to say that it's 100% forbidden, nobody ever does it ever, except in exam questions. Okay, so the other trick question that is very often there and I want to warn you about is that instead of giving you a value of x equals 230 and asking you for the value of y, sometimes they will give you a value of y and ask you for a value of x. And then you might think, well, I'm going to put the 230 in the vertical axis and see where those two things intersect each other, giving me a value of 223. But don't do it. This is the mistake. If you do that, you've exactly fallen for the trick that they're trying to make you fall into. That's not how you do this. So I have here a regression line that was built by considering x as the independent variable and y as the dependent variable. So that is the only direction in which I can use this line to make a prediction. I can put a value of x and see what happens to the value of y. I cannot do it backwards. If I want to do it backwards, I have to go into the linreg screen again, switch around the L1 and L2 here like I was showing you before, and get a new line to then put that value of y as the independent variable in this new line and see what the answer is. And I know that when you first hear that, it sounds really strange. Like, I already have a line of best fit. So if I can put a number of study time hours here and get a grade there, why can't I just do the same thing backwards? Put a grade here and find the corresponding number of study hours. So it does feel weird, but it's going to make more sense if we consider the cases where the correlation is very small. So for example, for grades and height, I don't have a line of best fit going up as in positive correlation or down as in negative correlation. I'm basically going to get a line that is horizontal. Because since these things are not correlated, whatever grade that you tell me you got and you ask me to guess how tall you are, I have no information. So I'm not going to guess very tall, assuming you got a good grade, okay? I'm not going to guess that you're very tall because you got a good grade, but I am also not going to do the opposite and get your good grade and predict that you're short, because that doesn't make any sense. What I'm going to do is whatever grade you tell me you got, I am just going to predict your height to be the average height of all of my students, because what do I know? My best guess is the average. So that argument should have convinced you that for things that are not correlated at all, the regression line should not only be horizontal, but it should have the value of the average of the other variable. Okay, so it's not going to be this horizontal line, but it's going to be kind of like this. It's not going to be perfectly horizontal because the points are never as perfect as to give a perfect zero for correlation. So it's going to have a tiny little slope going one way or going the other way, but it's not going to look like this. So I hope you can see the problem here. If this is the line for predicting height from grade, which is almost horizontal like we were just talking about, then this line cannot be used to predict grade from height. Because if you're tall, the line is going to be, well, it's going to go this way, right? So you're going to predict a value of grade that doesn't make any sense. And if you're a little bit shorter, then this one is going to predict that your grade is also too big. And if it was perfectly horizontal, that's even worse, because you're not going to be able to find the line in the horizontal for the height that you are. So in this case, the regression line made for height on grade does not work to predict grade from height. And again, because these things are not correlated, if you only tell me your height and ask me to predict your grade, again, I have no information, so I'm just going to tell you that I predict the average. Because then I have less chance of being wrong, right? Maybe you got more, maybe you got less, but I'm going to predict the average and minimize how wrong I'm going to be. And that is basically a vertical line. Again, not completely vertical because it would be very unlikely for the correlation to be a perfect zero, but they are two different lines. And if they are two different lines in the uncorrelated example, then they also have to be different lines for all the examples, because the process needs to be the same for all of the examples. So pretend that the pink one is, as we were talking about, the line of grades on study time. Now I have another slightly different one, which is green, which is to predict study time based on the grades. both of them look kind of good with the points, right? Visually, you don't have much of a reason to prefer one over the other, but the calculator knows how to calculate distinctively one or the other, depending on what you ask it to do. There is a point here that I've marked in black. It is the intersection point between the two lines, and it must be an interesting point, right? Let's think about that point. Coming back to the uncorrelated example, I told you that for any grade, I would predict the average height, and that for any height, I would predict the average grade. So the pink line is the horizontal line, y equals average height, and the green line is the vertical line, x equals average grade. The intersection point where they meet each other has both of those. The x is the average grade and the y is the average height. So there you go. The coordinates of the intersection point are the averages of both variables in the data set. So for all of the points. And again, this cannot be true only for the uncorrelated case, right? It is the same process. So for any case that you look at, the intersection point between both of the regression lines is a point that has this feature. The x coordinate is the average of the study time here, and the y coordinate is the average of the grade. This is a fun little fact to know, and it is often explored in IB exam questions. Okay, so now I want to show you some questions that explore all of these tricks and these details. I'm going to start with this one, which is one of my favorite questions about this topic because it is a paper 1 question. And a lot of people are surprised that this kind of thing can happen in paper 1 because we don't know how to calculate a line of best fit by hand. We need a calculator for that. We don't know how to do Pearson's coefficient by hand. We need a calculator. But even so, they can still write paper 1 questions about it, just as long as they don't ask you to do the things that the calculator would be necessary for. And this question starts with just a box and whiskers graph. He asks about outliers. You would do your IQR times 1.5 thing that you know how to do. And then he gives you the regression line. See, he's not going to ask you to come up with it because you don't have a calculator, and also because he hasn't given you a data set, okay? You don't have anything that you need to make a regression line, but he is giving you the regression line. So in this question, your job is not going to be to find the regression line, but to know what it means and to know how to work with it, what to do with it. In fact, he is giving you 2 regression lines. The first one, a equals 7/4 c plus 20, treats c as the independent variable and a as the dependent variable. And then on the next line, you have c equals half a minus 9, which is the other way around. A is independent and c is dependent. And then item BI says the adult is 42 years old. Estimate the age of the child. So the adult is variable A, okay? So what this is testing is if you're going to substitute A equals 42 and find the value of C in the correct equation, because he's giving you A and asking you for C, which means that A is independent, C is dependent, which means that you have to use the second equation that he gave you. Because if you use the first one, you will find a kind of similar value, but it's not going to be exactly the same. So it's going to be wrong. This is exactly what he's testing here, if you know which one of the regression lines to choose for this type of situation. And then B2 explores the other thing that we were just talking about, because he asks for the mean age of the adults, and we don't even have all the ages of the adults. So you feel tempted. I know how to calculate mean. I want to add them all up and divide by the number of adults, but I don't have that information. So this is not what the question is about. This question is testing if you know that other fact that we were just talking about, that the 2 regression lines intersect each other at a point that has the mean of one variable and the mean of the other variable. This is precisely what he wants to see if you know in this question. Because he gave you the 2 lines, it's easy for you to find their intersection. It's just a system of 2 linear equations. And then you know that the mean age of the adults is going to be the A in the solution of that system. If you wanted the mean age of the children, you would also get the C from the solution of that system of equations. Here's another question. This one looks more traditional. It is paper 2. It gives you a list of values. Starts by just asking you to calculate a line of best fit. Okay. But you have to notice that in part A, the line that he is asking you to find is x equals ay plus b. So from the data set of x and y that he gave you, you have to know that you have to treat y as the independent variable and x as the dependent variable when you choose in the linreg screen what to put in x list and y list. So again, he's testing the same thing as the previous question. He's testing if you know about the difference between the two regression lines. This time he's doing it in a slightly more traditional way with actual numbers for you to calculate. And then in part B, he talks about the other line as well. Let L2 be the regression line of y on x. This is a type of language that he can use. Y on x means that y is vertical and x is horizontal. Okay, so y on x, y is dependent, x is independent. This is the other line. In part A, he was asking for a line x on y. So x here, y here, x dependent and y independent, which matches what he said, right? X equals ay plus b, like we were talking about. Okay. But in part B, he's now asking something about the other one. So he wants you to consider both at the same time. And he says that the lines L1 and L2 pass through the same point with coordinates P and Q. Again, what is this point? The intersection of both regression lines. It is the point that has the average of x and the average of y. So those are going to be the numbers P and Q that he's asking you for. He didn't want to write it as x bar, y bar coordinates because that would just be giving you the answer, right? So he called them P and Q, but they are x bar and y bar, the mean of x and the mean of y. So you can go into the 1 var stats or the 2 var stats, or you can add them up and divide by 7 by hand if you want. In any case, you're calculating the mean, and that is the answer. Okay, this particular question can also be solved in a longer way by actually calculating the second line as well, since you've already calculated the first one in part A, and then you will have the equations of both lines. You can make a system and find the intersection point. This works. This is a valid solution to this problem that bypasses knowing about the intersection point being the mean of the coordinates of the data set. But it is a longer path. It's not exactly what he's trying to test, which is why I like the first question better than I like this one, because in the first question, you don't have any other option. You actually have to know the content in order to do what he's asking you to do. Okay, so question 3 gives you a set of data, starts by asking you for Pearson's coefficient. Very easy. These types of things often have 2 marks, even though the answer is just giving a number. And I think it's just because they know that it takes some time to type everything carefully in the calculator. So don't worry about that. You are just supposed to give the number. And then he says, interpret in context the value of R. This is a different word than the one I was talking to you about in the beginning of the video. I was talking about how to answer the word describe. But interpret is also a good word. He wants you to say whether it's strong or weak, positive or negative. And make sure you pay attention to the word in context, because if you say something like the variables are strongly correlated, this might not fit what the mark scheme expects, because you said the variables in a very generic way, and that's not looking at the context. So I would say something like the age and the blood pressure are strongly correlated. I'm assuming it's strong, but I haven't calculated. That would depend on the value of R. Then he asks you to make the regression line P on T. That makes sense because I think it is the blood pressure that depends on age and not the other way around. If you get higher blood pressure for some reason, you don't suddenly become older, right? So he is asking you for the appropriate line. Find the equation of the line. Again, at this point, you probably already have it because you've calculated the Pearson's coefficient and the information comes on the same screen. Now he's going to start asking you to make predictions. A 50-year-old patient enters the clinic. Use the regression to predict the pressure. You just put it into the line P on T that you've just calculated with T equals 50. And then the next question, a 16-year-old enters the clinic for his appointment. Explain why the regression equation should not be used. Listen, they are never going to ask you to do the same thing twice. So you've just calculated a value for 50. They're not going to ask you to do the same process again for 16. And he's not asking you to. He's asking you why you cannot do it. So you get back to the data and you see that the youngest patient here is 21 years old. So 16 is an extrapolation. And that is the answer. You shouldn't do it because it is an extrapolation. You don't have to put too many words and write a paragraph, okay? Just make sure that it is a straightforward sentence and that it contains the word extrapolation. Okay, so here's another similar looking question. You have a set of data. He's going to ask you for the regression line. This time it is the number of customers and how long I'm going to have to wait for my coffee at the coffee shop. Of course, the time is the thing that depends on the number of people there, not the other way around, and that is exactly the way that he's asking about it. But then he's asking you on the last line on the screen here to interpret in context the value of A found before. And this question can feel like a trick question if you're not paying enough attention, because usually when he says interpret in context, it continues as interpret in context the value of the Pearson's coefficient, which is exactly what we just did in the previous question. But that was not the question this time. He's asking a different question. So if you just go by like muscle memory and don't read until the end, you're going to answer the wrong question. This time he wants you to interpret in context the value of A in the line y equals ax plus b. And then even if you did read it carefully and you know that A is the slope of the regression line, and then you write that down, A is the slope of the regression line, that can still be considered a wrong answer because you didn't put it in context. You didn't use the variables, number of customers, and waiting time. So this question is kind of testing if you still remember what slope means conceptually, or if for you slope is just the number that multiplies the x in the equation. So slope is the rate of change, right? And slope in this case is how much more time I'm going to have to wait for each extra customer that is waiting ahead of me. If you wanted to say a similar type of sentence in the previous question, just to practice, because he didn't ask you that, the slope here would be how much the blood pressure is greater for each year that the person is older. So I'm basically just saying rise over run, which is what slope is, but I'm saying rise over run in context. Yeah, and then the coffee question asks you to make a prediction, which is totally valid because it is interpolation, and that's it. Those were all the little details about correlation, line of best fit. I hope you can remember all of them because the questions don't vary a lot. It's always pretty much the same thing. The only one I've ever seen which is a little bit more creative was this one that I showed you in the beginning, but still, it's addressing the same things.